Hello dear friends, a great welcome to this series on engineering mechanics. Myself is Jayarajan P. This is class 9 of the series and it includes topics such as introduction to dot product, which is essentially a part of vector algebra, then the methodology to be used for the computation of moment of a force about an axis in this scalar format, and finally some relevant solved examples. So let us start our class. So before starting our discussion on the computation of the moment of a force about an axis, let me introduce you to an important operation available in vector algebra known as the dot product operation. Because this operation is very much needed for the computation of moment of a force about an axis, in particular in the vector approach. So this presentation provides you only the moment of a force about an axis in the scalar format. The vector format will be presented in the next class. So let us go ahead with the definition of the dot products. The dot product of vectors A and B is written as vector A dot vector B. It is defined as the product of magnitudes of vector A and vector B and cosine of the angle theta between their tails. So referring these figures, we have two vectors, vector A and vector B, such that the tails are inclined at theta angle, and we have vector A dot vector B as A into B into cos theta. So from this definition, it is very clear that the dot product results in a scalar quantity. Accordingly, the dot product is also sometimes referred to as the scalar product. Please remember that theta always lies between 0 and 180 degrees. And the dot product operation respect the following laws. There is a commutative laws which says that A dot B should result in same as vector B dot vector A. Then considering the multiplication by a scalar, we have A into vector A dot B should provide us A into vector A dot vector B, which is the same as vector A dot A into vector B. Now coming to the distributive law, we have vector A dot B plus C can be written as vector A dot vector B plus vector A dot vector C. Now let us apply the above formulation in obtaining the dot product of any two Cartesian unit vectors. For example, suppose we are interested in calculating I dot I. As per the above definition, this is nothing but magnitude of I, that is 1 into magnitude of I, that is 1 into cosine of the angle between these two vectors, that is cos 0, that is 1. Similarly, let us go ahead with I dot j. So that is equal to 1 into 1 into the angle between I and j, it is 90 degrees. So cos 90, that is equal to 0. This indicates that the dot product operation on two same vectors, on same two unit vectors, will provide us a result equal to 1, and the dot product operation between any two normal vectors will provide us a 0. Okay, so accordingly a dot product operation is also effectively used to check whether any set of given vectors are normal to each other or not. Now suppose that vector A and B are available in the Cartesian format. In that case, we can write down vector A dot vector B as AXI plus AYJ plus AZK dot BXI plus BYJ plus BZK. Now referring to our earlier discussion on the dot product of the unit vectors, first of all we can expand this and we can collect all the dot product operation between the various unit vectors, and we know that any two same unit vectors should provide us a dot product equal to 1, and any other two dissimilar unit vectors should provide us 0. So applying that, we have I dot I will be 1, j dot j as 1 and k dot k as 1, and all other operations, for example I dot j, k dot I, j dot I, everything should produce us a 0 result. Using this, we can simplify this expression, the above expression, to ax bx plus ay by plus az bz. This means that the Cartesian, that means the dot product of any two Cartesian vectors can be obtained simply by multiplying the xyz components and sum these components, okay, algebraically. That means look here. So we multiplied the x component of a and b, that is ax and bx. Then we multiplied the y component of a and b, that is ay and by. And then we also multiplied the z component of the vector a and bz and obtain its product. And then we sum up what we call as the product of the xyz components of these vectors, and finally this will result in the value of a dot b. Now, as I told you, this dot product is extensively used to check or to find out the angle theta between the tails of any two vectors, which can be written using our above expression. We know that a dot b is nothing but a into b into cos theta, according to which theta can be written as cos inverse of vector a dot vector b divided by ab. This indicates that if vector a dot vector b happens to be 0, then what will be theta? Theta will be cos inverse of 0, that is 90 degrees. So that vector A will be perpendicular to vector B. So this is a very important check. We can check whether any two given vectors are normal to each other by just calculating their dot product vector A dot vector B. If vector A dot vector B happens to be 0, we can conclude that the two vectors are normal to each other. Another very important application of the dot product operation that is extensively used in engineering mechanics is to find out the components of a given vector along, that is parallel to a line, and perpendicular to a line. To demonstrate this application, I have shown here a vector O, vector A, and obviously this length will be A. And we would like to find out the component, the magnitude of the component of this vector A along two lines. One line is AB, and there is another line N that is normal to AB. So now let us find out how to obtain the component of vector A along AB, along the line AB and along the line N. Remember that AB and N are perpendicular to each other. Accordingly, we are talking about the rectangular components of vector A. Now, referring this figure, obviously we know from our earlier discussions, means that in the previous classes, how to obtain the rectangular components. We know that the magnitude of the component of vector A along the line AB can be written as this length will be A. So if this length of the vector is A, obviously its component, magnitude of its component along AB will be A cos theta. Now let us find out how to obtain this magnitude of the component through the dot product operation. So for the purpose, what we do is we carry out a dot product operation between the vector A whose component is to be obtained with the unit vector along the line AB, in which we would like to obtain the component of vector A. So we are performing a dot product operation between vector A and the unit vector along AB. Let me denote the unit vector along AB as UAB. So vector A dot vector UAB. As per our earlier definition, this is equal to magnitude of vector A, that is A, into magnitude of vector UAB. You know that UAB is a unit vector. Accordingly, its magnitude should be 1 into cosine of the angle between these two vectors, vector A and the unit vector in the direction of AB. Okay, that is obviously cos theta, where theta is the angle which vector A makes with the line AB. So that is A cos theta. So we find that this value A cos theta matches with the magnitude of the component vector A, which we calculated as A cos theta. This means that the magnitude of the component of any given vector, vector A, along a line. So here I would like to write down the magnitude of the rectangular component of vector A along a line AB is determined as the dot product between the vector A and the unit vector, vector UAB, defining the direction of line AB. So this can be described in the nutshell as, if we would like to calculate the magnitude of a given vector A along a line AB, first of all, we need to calculate the unit vector along the line AB, which obviously defines us or provides us the direction of the line AB. And then what we need to do is we need to carry out a simple dot product operation between the given vector A and the unit vector along the line AB. The result will provide us the rectangular component of vector A along the line AB. Now, obviously, knowing the magnitude of vector AAB, which is nothing but the component of vector A along the line AB, we can write down vector AAB, that is a vectorial component of vector A along the line AB as the magnitude of vector AAB, which is obviously a cos theta, into unit vector UAB along the line AB, because we know that any vector can be written as its magnitude multiplied by the corresponding or associated unit vector. Now once we know vector AAB, we can easily find out the magnitude as well as the vectorial definition of vector AN, that is the component of vector A along the line N, which is normal to the line AB. So this can be obtained easily from our definition. Vector AAB plus vector AN is equal to vector A. Vector A is known to us, vector AAB is known to us from this equation. So it does mean that we can straightaway obtain the vectorial expression for vector AN. So once we know vector AN, obviously we'll be able to obtain its magnitude as well, right? Now, having understood the basic properties and the definition of the dot product operation, we shall now start with our main topic, that's the moment of a force about an axis. So as I already told you, this tutorial or this session will cover only moment of a force about an axis, strictly only in the scalar format. Next class we will see how to do the same thing in the vector format as well. So in order to explain the relevance of moment of a force about an axis, here I have shown a very beautiful picture which is straight away taken from R.C. Hibbler's textbook. So here, as you can see, that this is a car tire, and we know that this car tire will be fitted to the rims using the so-called lug nuts. So let me zoom it. These are the nuts that is used to connect the rim with the axle, right? So here, as you can see, here is shown a wrench, that is an L-shaped tool, and this L-shaped tool, that is a wrench, that is used to unscrew the lug nut at the point O. As you can see that here, to unscrew this, we need to apply a force upward at the end of this handle. Now let us see what will be the moment of this applied force. Okay, so the magnitude of the moment of the force F about the point O, this we have already discussed in the last session. So the magnitude of this moment, magnitude of the moment produced by the vector F about the point O is nothing but the magnitude of F into the moment arm D. Remember that here the distance D is measured from the point O perpendicular to the line of action of vector F. Okay, so we know the magnitude of the moment vector produced by vector F at the point O as F into D. Now, as I already told you, this is the vector MO, that is, just a minute. Yes, so the moment of the vector F about the point O, this moment vector is denoted by vector MO. Now, I have already defined the magnitude of vector MO, which is nothing but magnitude of F into D. Now, please refer the discussions we had in the earlier class. Now, we know that this moment vector at the point O, it will be normal to the plane containing F and D. It should pass through O, and its sense and direction should be decided based on the right hand rule. According to that, we know that here vector MO should pass through the point O normal to the plane containing D and F, and it is directed outwards from the point O as shown here. Now we know one very important thing. Here, why did we apply this force F at the end of this handle? We want to loosen the nut O, the lug nut that is placed at the point O. So we know that this lug nut it can rotate only about the y-axis. Am I right? Because its position is such that it is a constraint to rotate. This nut can rotate only about the y-axis. What does this mean? This means that the total moment MO that is computed at the point O is not fully effective. It is not fully effective in loosening the lug nut at the point O. So, in calculating the useful turning effect that is produced at the lug nut, we need to calculate the component of vector MO along the y-axis. Only that will be very much useful for us for creating 100% effective loosening of the lug nut at A. So let us calculate what is that useful component of vector MO which is effective in loosening the lug nut at point O. Obviously, this useful moment is nothing but it is a component of vector MO along or about the y-axis. About the y-axis. How do we obtain it? It is very simple. We can do one thing. This is our diagonal. Vector MO is the diagonal. So from the tip, what we can do is from the head of this vector MO, we can draw two lines, one parallel to the x-axis and the other parallel to the y-axis. So accordingly, we can find out the component vector my that is effective in loosening the nut, which is marked here. Now what will be the magnitude of my, that is the moment about the y-axis? It is nothing but magnitude of MO into cos theta. If this is angle theta, this should also be angle theta. So it is nothing but vector MO, that is MO into cos theta. So magnitude of vector my, that is my, is equal to magnitude of MO, that is MO into cos theta. This is what I have written here, that is my is equal to MO into cos theta. Now we know that the magnitude of the moment produced about the point O, that is the magnitude of the total moment, that is Fd. That means My can be written as Fd into cos theta, which can again be written as F into d cos theta. What is d cos theta? Referring this figure, we find that d cos theta, it is nothing but the distance of the line of action of this force, okay, measured from the axis y. Alright. So thus we conclude that the magnitude of the moment of the applied force F about the y-axis is My is equal to F into dy, where dy is the perpendicular distance, okay, of the line of action of the force F measured from the y-axis. And obviously we can use the right hand rule to determine the direction of My. In this case, obviously we know that the direction of My, it is directed along the positive y-axis. So this is all about the definition of the moment of a force about an axis in the scalar format. So to conclude our discussion, we find that the moment of a force, okay, the magnitude of the moment of a force about an axis is equal to the magnitude of the force F into dy. Don't use d but use dy, where dy, as the term indicates, is the perpendicular distance measured from the axis y, okay, to the line of action of the force F. So, and the direction of this moment about the y-axis can be straightaway obtained from the so-called right hand rule. So let me illustrate the computation of the moment of a force about an axis in the scalar format using one very simple example. It's a very simple example, but this example will give you some more additional details, or you can note down some observations from every solved examples. So let me first of all read this example 1. It says, determine the resultant moment of the three forces as shown in the figure about the x-axis, y-axis and the z-axis. Look here, as you can see, this is the problem essentially consists of a box. This is a box, and as you can see that this box is subjected to three forces marked as F1, F2 and F3. And please remember that to solve any problem in engineering mechanics, first of all, we need to establish the location as well as the direction of our reference XYZ axis. In this case, as you can say that the origin of the XYZ axis, okay, it is chosen at the midpoint of this side, and the Z axis is made to pass through the front face of this block. Okay, so this is my origin, this is the positive X axis, this is my positive Y axis and positive Z axis. Now remember that we are given the location of the points A, B and C at which the forces F1, F2 and F3 are applied. So we are asked to calculate the moment, the total moment produced by the forces F1, F2 and F3 about the x-axis, about the y-axis and about the z-axis. So let us go ahead for the calculation. So let us first concentrate about mx, the computation of the moment about the x-axis. So here, as you can see that as far as x-axis is concerned, let us check whether F1, F2, F3 are effective in creating the moments or not. So the moment produced by F1, the moment produced by F1 about the x-axis, does this produce any moment about the x-axis? Obviously. So we know that the moment is the magnitude of the force, that is 60, into the perpendicular distance of the line of action of F1 from the x-axis, that is the 2 feet. And look here, this creates a counterclockwise moment. Accordingly, using the right hand, this moment produced by F1 about the x-axis, it is directed along the positive x-axis. So we have the moment produced by F1 about the x-axis is plus 60 into 2. Now let us calculate the moment produced by F2 about the x-axis. And here again we know that yes, F2 will create a moment about the x-axis. And what will be this moment? It is 50 into the distance, that is 2 meters. That is the perpendicular distance of the line of action of the force F measured from the x-axis. And here again we find that F2 produces a counterclockwise moment, indicating that for a counterclockwise moment, this moment vector is directed along the positive x-axis as shown here. And the moment produced by F2 about the x-axis will be 50 into 2 feet. So that is 50 into 2 feet. Now let us get into the computation of the moment produced by F3 about the x-axis. Here there is one very important thing. As you can see, the line of action of F3, it is parallel to the x-axis. And remember that when the line of action of a force is parallel to a given axis, it do not produce any turning effect about this axis. So accordingly, as F3 is parallel to x-axis, it do not produce any moment about the x-axis. Accordingly, we have written as a 0. So summing up the moments produced by the individual forces F1, F2, F3 about the x-axis, we calculate the total moment of F1, F2, F3 about the x-axis as 220 lb feet. Now this positive sign indicates that the total moment will be counterclockwise. Counterclockwise means that this moment vector will be directed along the positive x-axis. So now let us apply the same technique for Fy, the calculation of the moment about the Fy. Now here again we start with the forces F1, F2, F3. So what will be the moment produced by F1 about the y-axis? As we know, F1 is parallel to the y-axis, so it do not produce any moment. So the first term is 0. Now let us talk about the F2 force. Now from y-axis we know that the line of action of the F2, it is 3 feet. And again we know that about the y-axis, it creates a clockwise moment. A clockwise moment means that this will be directed along the negative y-axis. Accordingly, the moment will be minus 50 into 3. So this is what is being written here, minus 50 into 3. Now let us calculate the moment of F3 about the y-axis. It is nothing but 40 into 2. Again it is clockwise, so minus 40 into 2. That means the net moment will be minus 230 lb feet. The negative value indicates that the net moment produced by F1, F2, F3 about the y-axis, it is in the clockwise direction, or in other words, it is along the negative y-axis. Okay. Now let us talk about, in a similar way, the total moment produced by F1, F2, F3 about the z-axis. Now looking into this sketch, it is very clear that F1, coming to F1, we know that the line of action of F1, we just zoom it, the line of action of F1, it passes through the z-axis, right? It passes through the z-axis, means that my lever arm dy will be 0. Accordingly, F1 will not produce any moment about the z-axis. And the same is also true for F2. Regarding F2, we find that F2 is parallel to the z-axis, and accordingly it will not produce any moment about the z-axis. So finally, let us concentrate on the moment produced by F3. It is nothing but about the z-axis. It produces a clockwise moment, that is minus 40 into the distance 2. So it is minus 40 into 2, that is minus 80 lb feet. So the negative signs indicate that My and Mz act in the minus y and minus z directions. So this is all about this class. So we will come with a new topic, that is the computation of the moment of a force about an axis in the vector format in the next class. Till then, bye.